All right, hey guys, welcome back to gas laws. Today we're going to talk about Graham's law. Graham's law, you're not going to have to know a whole lot of information about Graham's law. I like to go slightly more in depth than the other teachers, but again, you're not going to be held responsible for the equation, except for the mini quiz. On the actual test, it's just more kind of theory for Graham's law. So here we go. All right, so for Graham's law, we're going to take gases that are going to be at the same temperature. So we're going to use our kinetic energy information that we talked about with kinetic molecular theory. So we have, gas 1, remember, it has the same kinetic energy as gas 2, right? That must mean we have half the mass, right? And then a velocity of 1 and velocity of 2, right? Remember, this time V stands for velocity, not volume. The little v is velocity, or rate of diffusion, okay? So since the temperature is the same, right? The kinetic energy of 1 is going to equal kinetic energy of 2. So here's our equation, right? We're going to just simplify it out. You don't have to know all these steps. It's just how you would derive this Graham's law equation. So take the square root of both sides. Okay, so Graham's law. Both gases have to be at the same temperature for us to identify the velocity or rate of either one. So the velocity of one, right, is going to be over velocity of the other one, is equal to the square root of the mass of the second one over the mass of the first one, okay? So for the mini quiz, I've dropped in this equation for you. And again, on the test, you do not have to know this equation. I just kind of like to go into it so you can kind of see the theory and mechanisms behind Graham's law, right? So in general, it's the bigger you are, the slower you are, smaller you are, faster you are, okay? So let's see it in a couple problems. All right, so Graham's law talks about diffusion, which is the particle movement from high concentration to a low concentration, right? Right, and then we have effusion, right? That's diffusion of the gas through an opening. Okay, so for gases, rates of diffusion and effusion obey by Graham's law, right? The bigger you are, the slower you are. The smaller you are, the faster you are. Okay, so here's a sample problem. Again, you're not going to be held responsible for the math except on the mini quiz. On the test, we're just going to be talking about the theory behind it, okay? So don't need to stress too much about the math problems, but I do kind of want to give you a little bit further information on it, all right? So on average, carbon dioxide travels at 410 meters per second at 25 degrees Celsius. We're going to find the average speed of chlorine at the same temperature, okay? So first we have to figure out, all right, what's our equation again? Velocity of 1 over velocity of 2 gives the square root of the mass of 2 divided by the mass of 1. So they're both at 25 degrees Celsius, so yes, excellent, we can apply Graham's law. Okay, carbon dioxide. How much does carbon dioxide weigh and how much does chlorine weigh? Okay, so first we're going to, instead of doing 1s and 2s, we're going to replace it with the actual elements. Okay, so now we're looking for the velocity of chlorine. We've replaced the velocity of carbon dioxide with 410 that we found in the problem, right? Where did we get the 44 from? Remember, carbon dioxide weighs 44 grams per mole. Where did we get the 71 from? Chlorine, right? Or it's diatomic chlorine, so it's 71 grams per mole. Okay, we plug it in our calculators. Well, first we're going to isolate the variable, plug it in our calculators, and we get 320 meters per second, okay? So not very hard work, right? We know how to use our calculators. Doesn't take very much. All right, again, easiest thing to do is put what you're looking for in the numerator. That's for any kind of math problem. All right, at a certain temperature, again, right, the temperatures have to be the same. So at a certain temperature, fluorine gas travels at 582 meters per second. And a noble gas, so we're not going to tell you what it is this time, a noble gas travels at 394 meters per second. We want to find what's that noble gas. Okay, so first we just, all right, who could it be? What's our problem? All right, velocity of 1 over velocity 2, right, over mass of 2 divided by mass of 1, square root of each. All right, so we're going to plug in fluorine, right, that's F2, which is 38 grams per mole. Definitely can't be helium because we can go ahead and take that out, right? Right? So why are we crossing these out, right? So if fluorine is 38 grams per mole, right? And it travels at 500, right? For it to be 394 meters, so it's got to be slower than 38 grams per mole, right? So that's why we crossed out the first two. It's got to be slower than 38 grams per mole because it's moving much slower than fluorine. And fluorine travels at 582 meters per second. For something to travel at 394 means it's moving slower, so therefore it's got to be bigger. Okay, so we've kind of done some powers of deduction. So let's do some math. Okay, so we're going to isolate some variables. All right, so we know the velocity of both fluorine and the unknown, and we're just looking for the mass of that unknown. Again, we're just plugging it into our calculator. So how do we get rid of a square root, right? We square it. We square both sides. And we get 82 grams per mole. All right, who is that, right? That is krypton. I almost said chromium. Axon, right? So again, it's not difficult math, but I just want to show you how we can figure out some of these problems. All right, so a different way we can word it. We have CH4, methane, moves 1.58 times faster than which noble gas? Again, how do we start beginning to figure this out? Well, velocity of 1 over velocity 2, mass 2 and 1. So how much does methane weigh? 16 grams per mole. Okay, so if that moves faster, right, then it has to be something that's going to be bigger, right? It can't be helium that's smaller. It's going to be something that's bigger if 16 grams per mole moves faster. Okay, so we just plug in what we know, right? Why did we put 1 over 5.8, right? Because it's moving 1.58 times faster. So we don't have to know the exact velocity. We just have to know the ratio. Square both sides, do our calculator work, and we get, right, 39.9 grams per mole. All right, obviously, who is it? It's going to be argon. Okay. And a stupid joke. Okay. All right. Last one. Another way we can think about our Graham's law, right? We have hydrochloric acid in gas form, right? And ammonia. Right? They're both released in this tube at the same time from opposite ends. Okay? The length of the tube doesn't really matter, right? But we're telling you it's, 1.2 meters of a tube. Okay? We want to know which way, where's these gases meet, right? A, B, or C. So what do we have to think about? We have to think about, okay, well, what's Graham's law all about? Graham's law is all about, right? The bigger you are, the slower you are. The smaller you are, the faster you are. Okay? So we have to figure out how much does each one weigh. We don't care how fast they're moving. We're caring how much does each one weigh, because then we can figure out who's going to get to each spot first. Okay? We're just going to do a guesstimate, right? So first thing I have to figure out is how much they weigh. Okay, hydrochloric acid, right? It's 36.5 versus 17 grams, right? Okay, so who is small, right? Hydrochloric acid is more massive, this is less massive. So therefore, that one's going to travel slower, this one's going to travel faster, right? So who's going to get to the middle first? Definitely going to be NH3, right? So where do we think they're possibly going to meet? Right, 17 grams is roughly twice as fast. So I think the best answer is going to be A. Right, if this one's moving twice as fast, right, this would be equal, right? So they're kind of ready to reach somewhere between A and B. Best choice would be A, right? I could ask you who's going to get to the middle first, right? The one that's going to be less massive is the one who's going to get to the middle first, okay? All right, so that is Graham's law in a nutshell. There's a little mini quiz for you to do to correspond to this, right? If you have any questions about it, feel free to email myself or Ms. Post, and then Have a great day. Again, you just have to remember just the theory behind Graham's law. All right, that is it for today. Bye.